Yes.
Okay. So basically, till now, what we have done is we have just taken two features and done the prediction. But when we come to real life, the data set is not like that. We have multiple features, and we have to find out a new our target variable. So in that case, what our equation turns out to be changes to y hat is equal to something of a sort that w0 plus w1 dot x1 w2 dot x2, and it goes on. What these x1 x2 means are, these are the features, the values of the features. For suppose say I have this feature, right? For say I have failures. So that is what the x2 means. And what w1 here exactly means is the coefficient of it, which we will be updating throughout for reaching the optimum thing. So what I want you guys to see is, I want you guys to have this equation on the back of your head. You just store it. I will be referring it again, time and again. So effectively, when you are actually doing any linear regression problem, when you are applying linear regression problem, there are only 4 to 5 major steps that you're going to follow. You're not going to do gradient descent. You're not going to find the cost function. You're not going to reiterate again and again. What you're going to effectively do is, the first process would be pre-processing. What exactly pre-processing means is, like for example, in this particular case, in this lab, we are dealing with the categorical values, and in the previous week's lab, we were dealing with the null values. So pre-processing, and it all also involves different things like normalization and etc., which is out of the scope of this particular lab. Then building the model, it is just a one to two line thing. And after that, seeing the loss that if you are getting a right loss, if you are getting a high loss, we will be optimizing it, and if you are getting a low loss, then it's nice, depending upon what our metric is. And after that, we will be predicting on the new data. Right. So when you're actually applying, effectively it boils down to only four major steps. So let's get started for this lab. So initially, what we are doing is all the functions that actually we need did, right, regarding the mean square error, building the model, initializing the weights, multiplying numpy arrays, etc., and building the linear regression model by, I mean, actually having the arrays, etc. All these things are bundled up into a very beautiful library known as sklearn. So sklearn has all the things you would actually want to do. It has different models. It has different metrics of saying, like you can calculate the accuracy, you can calculate different types of errors, etc. So that is what we will be using in this particular lab. And even if you actually do apply linear regression in any of the application based things, you will be using sklearn majorly. So as we know, numpy we are importing for small things, pandas for importing all the data we have, all the excel sheets we have into a data frame and doing operations with the data frame. Here what we are doing is, since we have to apply linear regression from sklearn has different models, right? It has linear models, it has different, for example, different models. So we, from linear models, so we are importing linear regression. And since our, for this lab, our metric is mean squared error, so from sklearn.metrics, we are we are importing the mean square error. If you want to find what all different things we have, you can go to the documentation and have a look at what all different metrics and models we have, right? So this is the imports we would be doing. Second, moving on, we would be reading the data set into a pandas data frame, right? So this is the csv file, and we are just simply importing it. So if we look at the data set that we have, this is a basic gist of it. We have these different columns, and the values look somewhat like this, right? Okay. So now coming to the pre-processing part. So we can also access the columns using the data. We have data, right? And if we just do dot of columns, we will get all the columns that we have. Okay. So now in this particular lab, we have to deal with the categorical values. What are categorical values? If I have to be precise, numbers, I mean features which don't have numerical values. If I have to talk in a very vague term, which don't have values like say 3, 4, or 25, 35, etc. It has values of this thing: yes, no, GT3, U. So those are categorical values, and we cannot, for a linear model, we cannot actually put them directly into the linear equation, right? So for example, we had that equation y hat is equal to ax1 plus bx2 plus cx3. So we cannot direct, if we send u, it is uninterpretable, right? So that is why we change it into numerical forms, either 0 or 1 or 2, whatever we want. So that is why we change the categorical values into different things. So majorly speaking, we have two different types of encodings. Before going to that, let's just see what all different types of values we have in the categorical variable set. So what I'm doing is, for ease of understanding, I've taken all the categorical values into a separate data frame. So what I've done here is, I've taken the data frame. I've selected D types which are not numbers. So if we simply do that, we'll get all the categorical values. So if we see over here, the address, the fam size, the reason, study time, etc., fam size, reason, study, schools up, etc., etc. So we will be getting that. And if we want to actually see what all different values we have, so I'm just iterating through this loop, and for a particular feature in the data frame, I'm seeing the unique values. I'll tell you why this thing is actually important. So why do we actually need to see the unique values, right? So I'll be coming to that. So, like I said, we have two major types of encoding. One is one-hot encoding, and another is label encoding. So, when we are actually dealing with this, or dealing with the data, we need to choose wisely what we want, what feature we want to one-hot encode, and what features we want to label encode. Right. So, for example, say we have a feature known as address. So address, we have, okay, let's take reason, it would be more clear. So for example, we have a feature called reason, and we have four different kinds of values in it. So if I if I label encode it, what exactly label encode means is, it will be assigning, starting from 0, it will be assigning an integer value to all of these things. So it will be assigning 0 to course, 1 to other, 2 to home, 3 to reputation. Right. And what one hot encode does is, for every feature we have, it creates a different columns. And for example, if a value has course, so it will be having one for that, and for rest of the columns, it will be having zeros. I'll show you how it comes down. Right. So now we have to choose between label encode and one hot encoding. So for example, we have this reason feature, and we one hot encode it. So it will be having 1 0 for this, 1 for this, 2 for home, 3 for reputation. So when we actually implement it, put it into the equation, what will have is, it will be little bit biased towards the reputation. The reputation will be having more weight to it. It will be having more priority to it. But in actually, that is not the case. So we don't have a reason that we need to have course, we need to give higher priority to reputation. In this case, we don't need to do that. All those things are equally important. Where label encode works is, for example, you are selecting, for suppose you are a firm and you are selecting people. So you have different values, say PhD, BTech, BS, and MSc. So in that case, you would be giving 4 to a PhD value person, and 0 to a BTech person, because obviously you want a person who has PhD, right? So you would be taking that. So in that case, we do label encoding. But in our case, where all of the things are equal, we if we do label encoding for reason, for a feature column like reason, it would not come out. It would be giving us a biased, or a biased result, right? And so that is why we would be doing one hot encoding for this. And for rest of the things which we have, say yes or no, so we can simply do a 0 or 1 for this. In this thing, we can label encode as a 0 or 1. 1 means yes, and 0 means it doesn't have there. So if we have a higher, and we have a value of say no, so if we will be having 0 on this, so eventually that particular variable would be eradicated. For example, ax1, y is equal to ax1, we had x1 as higher. So if we have the value as 0 and x1 we have 0, it simply goes off. And if we have 1, it means that it is present. So I hope the one hot encoding and the label encoding thing is clear, right? If is there any doubt in that?
Yeah, I have a question.
Mhm.
So when we like label encode columns with just no and yes, right? So aren't we indirectly giving more priority to yes only?
So that's what right now that is like, for example, we have yes or no. So if you have say 0, if you have the value as no, so you have 0. So it doesn't actually exist, it doesn't matter. So you're simply eradicating it. Right.
Yeah,
You
but
get my
but
point.
isn't this kind of subjective as in where we're placing our priority? Like in case if we want to say that no internet is better in terms of priority, so we should set no as one and yes as
Yeah.
zero,
Yeah.
something like that.
Yeah, so in label encoding or in different other types of encoding, you can actually, if you want, you can set that as well. So for this particular lab, we are not dealing with it. We're not just simply 0 or 1, putting it at 0 or 1. We are giving the thing to do it for the system itself. But in that, if you actually want to do it, you can actually do that.
All right,
Right?
thanks.
Okay, very good. So that's what. So for example, so I guess the concept is firm in your mind that for features like this, in which we have different more than values like course, other, home, reputation, and all of the things are of the same priority. One hot encoding is the best option, and label encoding doesn't make any sense. So for address, fam size, and reason, which have different values, we are using one
Rohan,
word. Uh,
yeah, I have a slight doubt. Means I am getting confused between bias and variance. What exactly is the difference?
okay. So bias and variance, can I take it towards the last of it? So I mean, it's a little bit off track of this thing. Like, I guess it will be eventually covered in
Like you
labs or
mentioned the bias. Like if we use one encode here, means label encode here, then it will
Hmm.
be biased. So
Okay,
that's
so
why I'm
what
getting.
I mean over there is, like, for example, if you have say you have 5 different values. So for fam you have 5 different values, and you have 4 values of address and 1 value of reason. 4 values of, for example, you have this reason thing. In this you have 4 values of course, and you only have 1 value of reputation, right? And this particular thing has been stated as 4, and this particular thing has been stated as 0. So don't you think whenever we'll get, well, the coefficient that will be set there, it will be changed, or it will be more inclined, or I'd say biased towards reputation? You're getting my point. So if I have to say course, it will be having some coefficient. And if I have to say reputation, which is having a value of 4, it will be having the coefficient will be less. I'd say A, if the coefficient is 1, the reputation is 4, then it will be, for example, it is aiming at 4. So then it will just keep the coefficient as 1. Whereas the coefficient should be greater than that. You're getting my point. For example, if you have 0 over here, or say 1, so should be greater than that. Uh, are you able to visualize that? Uh,
Yeah, but how is it different from variance?
I mean, when I said bias, I just meant bias as in, I'm speaking in literal terms. I'm not speaking in deep learning terms. Bias is a different concept. Bias, is your models going there? That's something I just used it as a priority thing. That's
I
not
think
a,
he got confused. I think he got confused between the machine learning term bias and the
huh,
subjective term bias. So
exactly,
Manohar
exactly.
was
Okay,
talking
you
about subjective
okay,
personal bias
yeah,
that people
Hmm.
have.
Yeah.
okay.
Yeah.
Means you didn't mean it literally.
No, no, I didn't mean in the terms of machine learning. Yeah.
Okay.
Yeah. Okay. So yeah, so it is clear that we have to one hot encode these values, and the rest of thing, we can label encode. So what I've done here is I've taken get dummies, I've taken the data frame, I've taken all these columns, and this prefix thing. What this prefix thing does is, for example, you have 2 values of r, 2 values of address, r and u. So address underscore r will be it will create a prefix of address underscore r, and it will create a column of address underscore u for the u values, and similarly for all other values of fam size and region, right? So that is what this prefix does. And yeah, get dummies, if you use get dummies, what it will do is, uh, if you have this thing, fam size, if you have gt3 and it will convert it into two different values, fam size or le3. Wherever we have the value as fam size, gt3, it will be having 1, and it will be having 0 for le3, and similarly for all other features. Okay, so yeah, it works like that. And now what I am doing is, from this, since we've dealt with these features, we're dropping these features from the categorical thing, and what now we will do is, for the rest of the features that we have, for the rest of the features like schools up, fams up, paid, etc., we will be label encoding it. So all those things are true or false, no or yes values. So we will be simply label encoding it. So it's a very simple thing. You import from sklearn.processing, you import label encoder, you create a object of it, and you apply label encoding to it. It's as simple as that, right? So it will be label encoding all of this. So this is the thing in pre-processing. That's all we need to do in pre-processing for this particular lab. After this, we have to split our data into into the features part and the target variable. So G3, since G3 is a target variable.
Manohar, sorry to interrupt, but have you like min-max scaled or standardized the numerical
No.
columns?
Yeah, no, I haven't done that. For example, I mean, it was for the extra part, right? It
No,
would
but
be.
like I understand that, but don't you think like that should be like a prerequisite for a linear model if you're doing that? And also, how have you dealt with? Are there any ordinal columns? Like, are there any columns in which there's a sort of an order, like 1, 2, 3, 4, 5, like that?
No, I didn't see that. I presume there's no thing.
Just check, because like if there are columns like that, you might need to normalize them as well, because in ordinal columns, this sort of order, like let's just say if you're rating a movie, it gives the movie a score between 1 and 5. So the
Mhm.
values 1 and 5 might be categorical, like 1, 2, 3, 5, 3, 4, 5, like discrete, but they
Mhm.
also hold, but their order or their magnitude holds some value. So in such cases, you might need to normalize them as well.
Okay, sure. Then I'll take that.
Just I mean, you can just no need to do it right now. Just carry on with it, but that can also be done. Like that
Yeah,
helps with the
yeah,
accuracy. Yeah.
yeah. Sure. Thank you for that. Okay, so for this thing, we'll be simply dropping for having our features, we'll be dropping our target variable, and we will be taking the target variable into y and the data set into x. So we are taking the linear regression model into an object, and we are doing model.fit. What this model.fit does is, it does everything that Vineet was speaking about in, for suppose, for 30 minutes. So it will be doing your predict function. It will be calculating mean square error for particular each of the values. It will be calculating the gradient. It will be updating the gradient, and it will be coming to the best coefficient. That is exactly, all those things are done simply by model.fit. Right. So if I do model.fit, it will search for the best weight, and it will be giving that. So if I, for every particular feature, if I print the coefficient, so you can see this is the coefficient that we got, right? So for age, the coefficient that we got was minus 0.6, and so on and so forth. And the intercept, so in Vinny talked about y is equal to mx plus c, the intercept. So this is the intercept that we are getting for this multiple linear regression model. Then if you have to calculate the loss, it is simply, we can just simply use the mean squared error and predictions and y. We are simply passing what the predictions that we got, and the y variable that was actually supposed to predict. So it will do the MSE, and it will return you the value. And the another task was predicting on new data. So we have this data, we are reshaping it into the desired thing, that was 1 comma 24. That is, we have one particular entry and it has 24 features. And if you want to predict, so then simply you take this model and you apply dot predict on the new data. What this model dot predict does is it has your values of say w0, w1, w2, etc., etc., and in the place of x1, x2, x3, it is putting this values, and it is giving you the y hat that you need, right? So one another thing, so if you want to actually see what our model predicted and what was the actual value, then I'm just simply taking the last 10 entries, and I'm predicting on that, just applying model.predict on the data that we have. And what I'm doing is I'm applying a for loop on the last 10 data sets and the predictions that we have. So the new predictions and the data of last particular 10 entries dot g3, which is our target variable, and we have simply printed it. So if you can see, this is what our model, this was what our model predicted, and this was the actual value. Yeah. So that was, I guess, pretty much it. Yeah.